Circuit components. In the previous unit, electricity, the following concepts were defined. Voltage, which is the amount of energy of a charge. Current, the movement of charges energized by voltage. And resistance, the resistance of a material to the flow of electric current. An electric circuit is an external path that charges can follow between two cell terminals. A cell is also known as a battery. The high voltage terminal of a cell is also known as the positive terminal. The low voltage terminal is known as the negative terminal. Current flows from the positive to the negative terminal. For charges to flow, the path must be unbroken. An example of a conductor used to form a circuit is copper wire. Continuing the water analogy from the previous topic, one can think of a wire as a pipe for charge to move through. A circuit is made up of circuit components. The cell or battery adds energy to charges when they pass through it. It provides the voltage to move the charges. A light bulb. You have a tungsten filament heated by current passing through it, transforming electrical energy to light and heat. A resistor reduces the current in the circuit. Ammeter and voltmeter to measure the current and voltage. And then a switch that closes or opens an electric circuit to allow the current to flow or stop flowing. There are many different types of switches depending on the application. And down here, there are many other circuit components, but they are for more advanced courses. And the positions of the ammeter and voltmeter in the circuit will be discussed later in this unit. The resistance of a wire was discussed in the last unit, the one on electricity. Lower resistance wires are preferred in order to ensure more current and energy is provided to light bulbs, motors, electric heaters, and many other applications. A resistor is placed in a circuit to reduce the current in the circuit. The current is reduced as circuit elements require different amounts of energy to properly function. Too much current can damage sensitive electrical components. Resistors heat up when current flows through them, transferring electrical energy to thermal energy. Drawing realistic pictures of circuits can be very difficult. There are common symbols to represent each component. This is a picture of a resistor, and here's the symbol we'll use on our diagrams. Here's a battery or a cell, and the high voltage terminal or positive terminal is here, and here's the low voltage or negative. The high voltage terminal has a longer vertical line than the low voltage. And finally, here's some wires, and that's kind of easy to draw. It's just a line. Circuit diagrams do not show where each part is physically located. It just shows where the current is flowing. Some more components. A light bulb has an X there. An ammeter and voltmeter have a circle with A for ammeter, V for voltmeter, and a switch. There's the switch. Right now it's open, and when it moves down to there, it would be closed. Let's draw a diagram that will connect two resistors with 3 ammeters and 3 switches. The switches are in the open position. Because the switches are in the open position, there's not a complete path for current to flow between the cell terminals. All 3 ammeters read 0 amps. Right? Current can't go through there. That's open. And if for some reason this was closed, it still can't go through the whole circuit because that switch is open. That's open, so if you don't have a totally complete path, no current flows. Same diagram, but close the switches in the middle and bottom wires. There's no current in the top wire, as there is not a complete path for current to flow from the high voltage terminal on the cell to its low voltage terminal. Right? There's no current getting through here, so this is not part of our circuit. However, this switch was closed, and this one was. So let's see if we can find a complete path without going through any open switches. We're following the red line, and yes, we get right back to the low voltage terminal. So current is flowing. Let's replace the resistors with light bulbs. And light bulbs behave just like resistors. Start with all 3 switches closed. There's a current in each light bulb, so they both light up. What if we open the top switch? Will the light bulbs both go out? No, the top light bulb will go out because there's no complete path for current to leave the positive side of the battery here or cell and get back to the negative side. However, there is a complete path here, so that bottom light bulb stays lit. These light bulbs are in parallel. More on this in the next topics. What if the light bulbs were in a row? Now the light bulbs are in a row, and we know that as series, which will be discussed again more in the next topic. With the switches closed, there is current in both light bulbs, and they are both lit. What happens if either one of the switches is opened? This time, with the switch open, there is no current through the circuit anywhere, because the current won't flow through an open switch here. So the current cannot get back, so it doesn't flow at all. That's why light bulbs in a home or office are in parallel from the previous slide. When any of the lights are turned off or if the light bulb breaks in a parallel circuit, the other light bulbs will stay lit. In this case, if any one of these light bulbs go out, the circuit does not have a complete path for the current to go through, and all the light bulbs go out. Example 1. Draw a simple circuit that has a 9-volt battery with a 3 ohm resistor across its terminals. What is the magnitude and direction of the current? Here's our two givens. And conventional current flows out of the positive terminal, that's the longer line, right over here, and enters the battery at the negative terminal, like that. So this red line here, that arrow shows the direction of the current, and then we use Ohm's law to find the value of it. So I is equal to V over R, 9 volts over 3 ohms, and we get 3 amps flowing through the circuit.